Good morning and welcome back. Last time we talked about Kirchhoff integral formula and we use a simple green function. Now, and we point out that the simple green function will have some problem. So we will remove the mathematical inconsistency. Before we start, I would like to review what we have learned so far. So let's go back to remember, we start from here, maybe here, Kirchhoff integral formula. And we separate the incoming wave into space-dependent and time-dependent separation of variable. And so this is Helmholtz wave equations. But remember, we can use another one, green functions, like this one. What will happen? If we choose a green function like this one, delta x minus s prime, and we let phi be phi, and psi, and phi equals g, and then substitute everything here, we got these relations. We talked about these issues before. If you forget it, you can come back. Yeah, you can come back and see the video again. So now we have two terms. Left hand side, we have only one terms, psi x. Left hand side, we have two terms. Okay, so for our convenience, we can choose a green function like this one. This is the simplest green functions if we have infinite space. If we have infinite space and at very far away, g contribute nothing. But now our problem is finite. That is, we have two surface. Surface 1 here and surface 2 here. Okay? Because we have two surfaces, so we can expect that we will have something inconsistent. Okay? So because of these green functions, we should consider this term. And another one, we should consider two terms. In the old days, we don't have to consider this term because this term should be small, should be very small. Okay. However, now we have to consider both two terms. We cannot use the boundary condition and say that on the surface it's zero. No, we cannot do that. We should consider everything. So we will consider this one, these green functions. And later on, I will show you this is not the best choice, but just a very good choice, not the best choice, because it will have some problem. And we can calculate gradient prime g, and we got these terms. Gradient prime g, we got these terms. And so we have two terms. One is here, the other is here, and we factor the common terms to the front. So we got this one. Okay, looks okay. This is the famous Kirchhoff integral formula. Everything looks fine. Kirchhoff integral formula. And then we will make two assumptions, two approximations. The first one is precise derivative on S1 is 0, except in the openings. Second, in the openings, they just like the incident wave. Yeah, without the obstacles. Okay, two assumptions, two approximations. That will simplify our calculation a lot. So it works remarkably well in optical domain and has been the basis of most of the work on diffraction. So we have two terms. However, we know they have mathematical inconsistency. First, phi, precise and precise normal derivative. Precise normal derivative vanish on any finite surface. If this one is vanish on any finite surface, then psi equals 0 everywhere. This is, of course, inconsistent with the second assumption. Second assumption tells us that at the opening, just like the incident wave without obstacles. Second, equation 7.10.79 does not yield the assumed value on S. The mathematical inconsistency in Kirchhoff approximation can be removed by choice of a proper green functions. Yeah, if you choose a proper green function like this one, GD for S prime on S, then we can, this one 0. So all we need to do is consider this term. That can simplify the calculation a lot. But actually, we still prefer this one. Okay, I will show you. Now, let me remove the mathematical inconsistency using a better green function. Not better. Maybe I should say on the surface is 0. Okay, that's Dirichlet boundary conditions. So how to remove the mathematical inconsistency in a Kirchhoff approximation? By the choice of a proper green function. If psi is known on the surface S1, a Dirichlet green function GD satisfies that on the surface S1. On surface S2, this is correct. However, on surface S1, the old green function, this one, is not 0. Okay. So we consider another one. So a generalized dielectric constant gives us this one. This is good when we consider a plane screen with apertures. So the screen is plane with aperture here, with a small opening, with a hole here. The method of image can be used to give Dirichlet green function explicit form. That is so we have source term, one the same, x, y the same, but one is in a positive z, the other is in the negative z. Okay, and consider this is the z directions. Okay, so we have two. Therefore, the green function will be rewrite into this form. Okay. However, we don't like these green functions. We still prefer the old green functions. This one. Because this one works well. Okay. So the old green function is not the best choice and will have some mathematical inconsistency. And actually, we can remove the mathematical inconsistency. Okay. Now, I will give you several examples. First, I will give you a special case. Less diffraction of a spherical waves. And we still use the old green functions. And a diffraction of a spherical waves. So there is a point source here. And that's spherical wave. And originate from a point source at PS. That's a point source here, generate spherical wave. And we use Kirchhoff approximations. 0, 0. And here, just like the source, without the obstacle. Okay. And so we have two terms. This one already know. Second, we use this one, gradient prime phi, and we got this one. Remember, we still use this non-perfect, but good choice. Good choice. Gx s prime equals e exponential ikr over 4 pi r. And substituting phi and 6 into equation 10.79. And assume that kr and krs, kr and krx much greater than 1, which means observer or source are very far from lambda. K is 2 pi over lambda. That means R is greater than lambda. Rs is greater than lambda. R is greater than lambda. Rs is greater than lambda. Okay? We obtain this one and negate high order terms. Okay? So we got this one. It's not finished yet. We still have to calculate. More cases can be found in Marian and Hield. Classical electromagnetic radiation following equation 12.14. Okay, so if you are interested, you can have a look at this textbook. I will give you another example. That is, we will use a scalar diffraction theory. This one agree with observations, although it is highly artificial. We assume a disk. So this is another example. Deflection by a circular disk. By a circular disk, we have a disk here. We have a source here. We have another source here. Okay? And we assume PS and P are on the axis of the disk. This is the axis of a circular disk, just like z directions. And Px and P are at equal distance. So here the distance is b. From here to here, the distance is b again. And on the axis, so this is the radius. Okay, so Rs equals R because on the axis, this point to the source, this point to the source, the same. The A prime, why we need to use the A prime? Because we need a surface integral on the S1 plane. This time, S1 plane is here, and equals 2 pi R dr, okay? And R squared equals R prime plus B, R prime squared plus B squared equals R prime dr prime equals R dr, because this is a constant. Hence, the A prime equals 2 pi R dr. Okay? Two pi R dr. From these relations, we know this one can be substituted into here, 2 pi R dr. Okay? So, n prime dot rx equals n prime is here. Propagation, the propagation of the wave in these directions. RSR, that will be minus cosine theta equals to minus b over r. N prime dot r. So one is in this direction, the other is in these directions. They differ by a minus sign. So this one give us a minus cosine theta. This one give us a cosine theta. Okay. Okay, so we got everything. We substitute this one into these equations. Substituting equation 8 into psi p ik over 4 pi surface integral. The a prime exponential, we have this term, and we got this one and this one. So eventually, from 7, we can calculate to 9. Okay, that is equal distance. So we have 2 r and rx the same. So we equals r squared. And surface, the r runs from the edge here. R equals d squared plus b squared square root. Okay. So, and here we got another one cosine theta. Cosine theta. This one minus this one. This one minus this one. So we have 2 minus signs. So therefore we can write into here. So we have IKB. Okay. That's what we have so far. And this one can be replaced by 2 pi r dr. And r cancel. So eventually we have this one. Okay. You can try to derive this equation by yourself. It's not very difficult. Then we will perform integration by parts. Integral from a1, a2, u dv equals, maybe I should say mu u dv equals uv a2 a1 minus integral. So it's just an integration by parts. So we have u equals this one and v equals this one. dv equals this one. dv equals this one. u equals this one. So by integration by parts, we got this one and this one, uv, okay, plus these terms. Okay, so we can absorb here to here. Therefore, it's 2ik, 1 over 2ik dr exponential 2ikr. Okay, that is this one times this one. Okay, and by doing so, we can 2ik r squared exponential 2ikr integrate from here to the edge of the circular disk to infinite. And another one is here, shown here. That is 2ik plus 1, and this one derivative give us a minus 2. Okay, so we got these relations eventually, and integral from d squared plus b squared to infinity. That's the integration by parts. Okay, so we got these terms. Which one is dominant? Which one? I think this one. No, not necessary. IKB. This one is shown here, and we have other terms. That will be negligible because KR is very large. KR is very large. So this one is small compared with this one. Okay, so we can simply omit these terms. So eventually we got 2d squared plus b squared. Okay, substitute this term into here, and I cancel. So we have B here, and how about K? K cancel. R squared, that is this one. 2 is still here. Exponential 2IKR. Okay, the same. So psi P is here. What is the absolute value? The absolute value square is the intensity. Intensity at P will be proportional to intensity. Intensity will be proportional to field amplitude square. So it's B squared over 4D squared plus B squared squared. Since IP greater than 0, for OB, there is always a bright spot at any point on the axis. What is the physical meanings? Let me show you again. We have a circular disk here. No opening, just a disk. And opening here. And we have point source here. And the wave will propagate in all directions. And eventually, at the equal distance, here, we will have a bright spot. That's a surprise. That's a huge surprise. Because the light is blocked by this circular disk. It counterintuitive our understanding. So it looks like it doesn't like true. Okay. Second, so we will discuss this idea very soon. So we have extra. You can explain what is the physical meaning, physical reason for that. Actually, we have explained in the previous 2 or 3 pages. Second, when D equals 0, that means the size of the circular disk shrink to 0. No circular disk at all. It should be the same as our previous understanding. Separation is 2IKR over 2B. In the limit of no obstacle, D equals 0, psi P reduced to the exact solution for a point source. That is the approximation in 10, because the exact solution in 12. What is the mathematical reason? So try to explain. I will give you some extra bonus. The diffraction pattern of a disk formed that's from Holiday, Resnick, and Walker. Note that Fresnel bright spot at the center of the pattern. The concentric diffraction rings, that's the concentric diffraction rings, are not predicted by equation 11, because which applies only to the fields on the axis. Equation 11 applies only to the fields on the axis. Okay, equation 11 applies, this equation applies to the field on the axis only. Okay, so you cannot predict the concentric pattern. Okay, so we have a Fresnel bright spot here, this one. This one is really a huge surprise. So I will tell you a story about Fresnel bright spot. So this page shows that a historical anecdote about the Fresnel bright spot. The following paragraphs are taken from Holiday, Resnick, and Walker. Diffraction finds a ready explanation in a wave theory of light. However, this theory originated advances, originally advanced by Huygens and used more than 100 years later by Young to explain the double-slit interference, was very slow in being adopted. That is, although Huygens said the wavefront idea and Young explained the double-slit interference, most of the people do not accept this idea because it ran counter to Newton's theory of the light was a stream of particles. Newton considered the light as a stream of particles. Young and Huygens consider they are wave natures. Newton's view was the prevailing view in French scientific circles. 法国的科学环境之下 of the early 19th century, when Fresnel was a young military engineer. Fresnel believed in the wave theory of light, submitted a paper to the French Academy of Science, 法国的皇家科学院, describing these experiments and his wave theory explaining of them. In 1819, the Academy, dominated by the supporters of Newton, he believed the light was a stream. I say was, that is a stream of particles. The light, supporters of Newton, that is particle-like, and seeking to challenge the wave point of view, organized by a prize competition. They want to challenge the wave point of view, organized by a prize competition for an essay on the subject of diffraction. Fresnel won this prize. Okay, the Newtonians, however, was neither converted nor silenced. They don't believe. One of them, Poisson, point out the strange result. The strange result that if Fresnel's theory was correct, then light waves should fly into the shadow regions of a sphere as they pass the edge of the disk, actually a disk, producing a bright spot at the center of the shadow. This looks like impossible. The prize continuously arranged a test of the famous mathematician's predictions and discovered that the predicted by Fresnel bright spot, as we call it today, was indeed there. People think, Poisson think, according to the mathematics, in the center they will have a spot, but there should be shadow, no spot. So they say this is incorrect. Fresnel's prediction is incorrect. However, from the experiment, they demonstrate Fresnel's prediction was indeed there. Nothing builds confidence in a theory so much as having one of its unexpected and counterintuitive predictions verified by experiment. That is, the theory predicts something unexpected and counterintuitive prediction. Unexpected and counterintuitive. But this one was verified by the experiment. That built confidence well. So Fresnel's wave theory was accepted quickly because Before that, people just think wave, a light just was a stream of particles. So it will in a direction. Yeah, ray tracing, ray optics. And now we show that. Fresnel shows that it's not. Okay, let me give you another example. Less famous Newton's ring. You can see here from Benson. When a lens with a large radius of curvature, this is the lens with a large radius of curvature, is placed on a flat plate. This is a flat plate, as in the figure below. A thin film of air is formed because large radius of curvature. So they will form a thin film air gap is formed when Newton is illuminated with monochromatic light, circular fringe called Newton ring can be seen. So it's illuminated with monochromatic light. So it's monochromatic light, 单调的 single frequency. And he will see that in the middle is not a bright spot. On the other hand, is a dark spot. It's dark spot. Not dark. It's dark, unlike Fresnel bright spot. So it's completely different story. Fresnel predict that in the shadow region we will have a bright spot. However, Newton's ring, on the contrary, use a lens, large radius of curvature, and there will a thin film of layer, and due to multiple reflections in this region, in this region, because of this thin film of air, they will have out of phase here. Okay, let's consider as extra bonus. Try to write down your understanding about Fresnel bright spot and Newton's ring, or the dark in the middle, Newton's ring, bright spot in the middle, in the center. Okay. Now let's move on to the last few slides of this chapter, section 10.8. We will talk about an interesting theory called Bobinet's principle. Okay, equation 10.79. We got this one. We use just traditional green functions, and we consider this term and this term. Okay, now consider if we have a point source, and this is screen, no diffraction screen, just an imaginary surface. We got everything. So phi p dashed surface. Okay, that's phi p. And now we have the first case. We have something here. We have a diffraction screen. It can be any shape. It's a disk or any shape you want. Okay, then we can detect phi p with A, condition A. Okay, we just integrate from here to here, from here to here. Then we have a complementary diffraction screen. It's completely opposite to this one. Here is blocked, now it's opened. And here is opened, now it's blocked. Okay. This one plus this one plus this one, we got nothing. Okay. sorry, the size, this one and this one is exactly the same. So we say it's complementary diffraction screen, SB, by Kirchhoff approximation on the obstacle, psi and precise normal derivative equals 0. Elsewhere, psi and partial n equals loss of the source. So here will be the same as here. That's Kirchhoff approximations. We have 2 psi. Therefore, you can imagine this one plus this one will be exactly like this one. That's so-called Bobinet's principle. Looks reasonable. Now let's consider another case, another example. We have a light beam of finite width. This light beam is finite width. That is just like a flashlight. We have a finite width, no screen here. So obviously you can imagine light just propagate in these regions, and outside nothing. Okay, now we have a screen here, or we have another complementary screen. So we have a screen here because of the obstacle, so they will generate diffraction form, and because of small opening, they will generate diffractions. So initially nothing. Now we have two. So obviously, according to Bobinet's principle, phi p equals phi a plus phi b equals 0. So phi a here will be equals to phi b. That is this case and this case just out of phase. Okay, now we still have 2 pages to go. We will consider so-called Fresnel diffraction and Fraunhofer diffractions, 2 conditions. There is a clear diffraction patterns only when R is greater than D. So that is, observer is far from the aperture, the size of the aperture. So in the integrals such as 10.77, R equals source and observer source can be approximated by R, because R is much larger than source terms everywhere except exponential IKR. Why exponential IKR, which cannot omit this part? Because this is source part. That's very important. We should consider, we talked about this issue before, where the phase angle KR must be evaluated more accurately. However, others you can omit. So let's consider 3 length scale, R, D, and lambda. R is the observer. D is the aperture, the size of the apertures. And lambda is the wavelength of the incoming wave. And R equals x minus x prime absolute value equals R squared minus 2 R prime cosine theta plus R prime squared 1/2 square root. Okay? And this one, according to Taylor's expansion, we move R to here. And 1 minus this one and this one. So we can use Taylor expansion This one, 1 minus 1 over 2. These terms, minus 1 over a. These terms square. And we keep this one here. And high order terms, this one, and this one. Okay. So we have first terms, second terms, third terms. Okay. The first term is if we times k, kr. Okay. Order of kr. Okay. That's the first term. Order of kd, because kd small, over kd square, large, small, extremely small. So if the third and high order term are neglected, we have the Fraunhofer diffractions. That's far field. Let's consider this one is R is very, very large. So this one contribution is very small. So Fraunhofer diffraction is valid for far field. If third term is kept, this one is kept, but higher order terms are neglected. Higher order terms are neglected. We have the Fresnel diffractions. Fresnel diffraction, consider this one is good for near field. Fraunhofer diffraction is good for far field. So you can just define the Fraunhofer diffractions for far field, Fresnel diffraction for near field. You can write a report to me and explain your understanding about Fresnel and Fraunhofer diffractions. Explain in more detail, maybe just one page. You got 1 point. Easily. Okay. Try to demonstrate. Show me your understanding about Fraunhofer and Fresnel diffraction. Okay, that's the end. But we will have one slide to show you when Mars rover shows that they observe blue sunset on the red planet. We know Mars is famous for the red planet. Mars is like fire, so it's a red planet. And however, close to the sunset on Earth, it should be red. However, on Mars, it's blue. Interesting. What happened here? NASA has a rover called Curiosity, 好奇号. Mars rover recorded this view of the sun setting at the close of the mission. 956 Martian day from the rover's location in Gale Crater, 裂谷. This was the first sunset observed in color by Curiosity. The camera see color very similar to what human eyes see, although it is actually a little less sensitive to blue than people are. Yeah, very similar to our eye than people are. A little less sensitive, but it's quite similar. Dust in the Martian atmosphere has fine particles. The particle will scatter the blue light. That permit blue light to penetrate. the fine particle allow the blue light to penetrate the atmosphere more efficiently than the long wavelength color. That means the fine particle is about the size of the long wavelength red light or ultraviolet or infrared. So it scatter long wavelengths, but short wavelengths is still okay. That's why the blue colors in the mixed light coming from the sun to stay closer to the sun's part of the sky compared to the wider scattering of yellow and red colors. So it's just like PM 2.5. If we have a series PM 2.5 problems, maybe it will scatter yellow and the red light. We will see the blue sunset someday. But it's not the good news. The effect is most pronounced near sunset, when light from the sun passes through a longer path in the atmosphere than it does at midday. So close to the sunset, blue light can penetrate, travel, can penetrate much further than the yellow and the red color. So close to the sunset, we will see a blue sky. That's blue sunset. Blue sunset. Unlike the Earth, we will see the red sunset. Okay, so completely different condition because Mars has fine particles. Yeah, that's the problems. So maybe at the Sahara Desert, we will see some kind of this phenomena, scatter the wave, if you have a chance. Okay, see you next time.